Hello, young astronomers. Today, we're going to talk about the history of astronomy. We're going to go way back to the ancient times, and we're going to discuss their understanding of the universe up until the time of telescopes. So, the data they had are the data that we've talked about this week, the things that we can see with our eyes. The apparent motions of the objects through our sky. Um, let's review, or this is a short preview for our other chapter here. Um, the sun moving across our sky, the moon moving across our sky, rising in the east and setting into the west. That has to do with the rotation of the Earth on its own axis. Um, the appearance, the stars in our sky, the constellations, while their relative uh, configurations stay the same, the Big Dipper looks the same, but it rotates. It rotates around a special star that's called Polaris. And we also learned that Polaris won't always be our North Star. Because the Earth wobbles a little bit back and forth, and so uh, the Egyptians had Tuban as their North Star. We'll have Polaris for another couple of hundred years, and then we'll have another North Star. But then in 26,000 years, it'll be back, and we'll have Polaris as our North Star. The reason why it doesn't rotate is because it's right above the axis of our rotation. So the stars rotate around Polaris. Again, over the course of a night, not that you could sit there and watch them do it, but if you come out an hour later, you'll see the constellations have kind of tilted a little bit. Or if you're just looking at a planet or the moon, it will have moved across our sky. All of that motion, and even the moon, even though the moon is orbiting the Earth, we can't see that on an hourly basis. It would, if we waited all night long, and we were just observing the orbit of the moon, it would move about one diameter actually across our sky due to its orbit. Remember, it takes 30 days roughly to go around. And so over the course of one night, you can't really, that's not what you see. When you come out at night, an hour later, and the moon is in a different spot, it's not because of its orbit, it's because of the Earth spinning. Let's stop there for a second and put ourselves in the places of early humans, even early scientists. It's quite natural to assume that those objects are all rotating around the Earth. Especially we talked about in week one. We can't feel that motion, so it doesn't feel like we're moving. When they ran, when they got on their horses, well, by the time we had cars, we had figured this out. But before that, you can tell when you were moving. They didn't have nice, smooth airplanes or cruise ships or things that to teach them that you don't really feel speed, you feel changes in speed. It was quite natural for them to think that. And we thought that for thousands of years, that everything, all of the motions in our sky could be explained and were explained, and to the technology at the time were actually well explained by the Earth being stationary and all of the celestial objects, the sun, the moon, the stars, orbiting around the Earth. We call that a geocentric model. We'll come to that in a second. There's another motion that has to do with our orbit. The Earth is going around the sun. Again, it would take you a whole year to notice that, right? And so the rising and the setting of the sun has nothing to do with that. None of the motions I just described have to do with our orbit, but let's say we were looking at a star. Let's say we're looking at the Big Dipper. The Big Dipper looks different. Not the Dipper configuration, but the tilt in the Big Dipper depends on what time of year we look at. The zodiac constellations, they rise and well, they don't really rise and set. They're on one side of the sun or the other, so that we can only see them during the nighttime. They're always there, but we can't see them during the daytime because the light from the sun blocks them out. So the ancients saw different stars coming and going, and they were patient. They actually, they took maps of the sky and they saw this repeating pattern. Um, and so those patterns that change on a monthly basis, a seasonal basis, have to do with our orbit around the sun. So we have two things going on, and then the phases of the moon are three. The relative configurations of the sun and the earth and the moon are the astronomy that we can see with our eyes, and the astronomy that the ancients could see with their eyes. And so we're going to talk about how they figured out what was going on in the universe by just using the information that they had with their eyes and their feelings on Earth. As I said, astronomy is the most ancient science there is. We see evidence of early humans' interest in the sky. This is a cave drawing from America, actually from Nevada, where we see what pretty obviously the sun, and that arrow is pointing from east to west. So we have a record that the ancients were very interested in the sky. This is one of the oldest cave paintings we've ever uncovered, 18,000 BCE, 18,000 years BCE. Well, those may look like horse droppings, but there are 29 of them, and that pattern is kind of like what we see with the phases of the moon, and how the moon is in a different part of our sky every night. So it's pretty clear that they were keeping track of the moon even 18,000 years before whatever you want to call that. BCE is what we call it these days. So astronomy evolves along with civilizations. It invariably starts off as some mysticism and/or religion, and as I said, I'm an old grizzled scientist, but it's still a mystical, magical experience for me to look at a deep, dark night sky. So I can certainly understand all that. The sun, for instance, is the center point of many religions. But then it goes beyond that. Even if you keep that part of it, it goes beyond that, and it can be used for practical purposes, keeping track of time, sundials, those constellations, those zodiac constellations allowed the ancients. Most of the early civilizations were all in nice, warm, tropical climates where they didn't get cold. They couldn't tell the season was changing by the temperature, but they did have to plant their crops at certain times because there were rainy seasons, for instance. And so they used the constellations the zodiac constellations in particular to tell what month it is. The zodiac, is based on being able to see those constellations during different months. It was used extensively for navigation. We talked about how the North Star always points north. We saw that the sun, it rises in the east and the west, but not precisely. It kind of moves around during the seasons, and so the stars are actually better to navigate with. Especially at sea, they waited till night. They could really tell where they were when it got dark, when they could actually see the stars. But then it evolves into a science. Humans have this innate ability, or this innate desire to understand everything, to kind of take things apart, either with our hands many times, see what's inside, how they work, or at least intellectually try to figure out this giant mechanism that is the universe. And many of the ancients really thought of the heavens, the celestial bodies, as a machine, as a giant, heavenly clock, cuckoo clock, or some giant machine that was moving the planets and the stars around. It's We still keep the practical applications of it. Certainly, we'll learn all sorts of practical things about astronomy. About we have to be careful with the sun. We have to at one point the sun is going to. We have to be careful on it right now with solar flares and things. We have to learn how to protect ourselves from it. The sun gives us life, but it also is trying to kill us. Not maliciously, but it is a dangerous nuclear furnace that is it's stable on a long term, not a very long term. We're going to learn that the sun is actually going to change, and with devastating effects for the Earth in billions of years from now. So at some point, we're going to have to get off this planet. But even there's even practical applications right now. Right now, we have a probe that is measuring the atmosphere of the sun. Imagine the technology that was needed to keep that thing cool, to insulate that from all of that heat. Well, that will be in your homes in another year or two. The camera in your smartphone was developed by astronomers to take better pictures of galaxies and stars. So it's not why we do it anymore. Well, I mean, maybe there are some astronomers who do it for practical reasons. I'm not one of them, but we do it because we want to understand. We want to understand everything there is to know about the universe. The earliest astronomers that we have a written record on, and it's written in stone, literally, were the Babylonians. Again, 17th century BCE. They had detailed charts of the sun, moon, and stars. They had a whole cosmology of how the universe was born. Their version of the Big Bang. Of course, it was very religious, but they had an understanding of an attempt at the understanding of how the universe worked and how it was created. They thought the Earth was stationary in the center of the universe. But even with it, it turns out that eclipses, phases of the moons, only really depend on the relative positions of the sun, Earth, and moon. So even if you think one of those is stationary, you could still you don't have to have the right one being stationary to predict when an eclipse will happen, to predict what the moon will look like the next night. And so they were able to do that. I mean, I couldn't predict an eclipse now without help of a computer. They didn't have computers. They didn't have calculators. It's pretty amazing what ancient humans could what they were able to decipher about the stars and the planets and the moon. And I can't think of a civilization, honestly, that hasn't contributed to astronomy. The Egyptians, the Chinese, the Mayans, Incans, indigenous people of North America, they all had extensive knowledge and patterns of the sky. There's an Aztec calendar, some more cave paintings from North America. The Egyptians built their pyramids to coincide with three of the brightest stars on the summer solstice, or the aliens did, but they had a knowledge of it. The people of Central Africa, 6500 BC, used the tilt of the moon to tell when to plant their crops, when the rainy season would come. The tilt of the crescent moon. Remember the tilt of the crescent moon. If you draw a line through it, it points towards south. Up here, they were able to tell what time of year it was. They really had an extension of that. Stonehenge, Machu Picchu, the holy buildings of North American Native Americans all had a connection to the solstices, or where the sun would be at a certain time of year or a certain time of day. Um, the Polynesians did not have maps uh, like the people who lived on land. There's no landmarks in the ocean. Maybe a couple of islands. They used this. They used the stars. That is a map, actually. That's not a map of cities or mountains or large trees or buildings. That's a map of the sky. Uh, and each one of those shells is a bright star. You don't use planets, we'll learn, to navigate, because planets don't stick around long term. But the stars in our sky, other than the effects that we just talked about, the rotation, the movement of the Earth, remember, they're very, very far away. So the stars in our sky, we have to go back to the records of the ancient Egyptians before we can see a star position actually changing. Even though they're going tremendous, hundreds of thousands, millions of miles per hour relative to some things, they're so far away we can't actually see that motion, at least with our eyes. So these are all practical reasons to study astronomy. Here's my favorite one. 1400 BCE in China. The Chinese astronomers made the first observation of a supernova explosion. Now, they didn't realize that it was a supernova. They didn't realize it was even a star. They didn't know what a star was, different from a planet, different from the sun. And they wrote this on the bone of an animal. They didn't have paper, but they made a record. They knew the sky so well that one star got much brighter. And then they kept track of it, and they watched it fade away. Pretty cool. One day, maybe you'll get to see a supernova explosion. There's a star called Betelgeuse. The movie was named after it, by the way, not the other way around. That is about to go supernova. And luckily for us, it is close enough that it'll put on a big show. It'll get brighter than the moon. Than in our sky for about a year and a half, and then it'll slowly fade away. And luckily, we're out of the danger zone. We're right; it's close enough for us to actually observe it with our eyes, and far enough away that we'll learn supernovas are very, very, very dangerous to be around. One or more of the mass extinctions in our past on Earth could well be correlated with a supernova explosion. We don't have solid evidence for that, but we'll talk about it. There is some correlation between our mass extinctions and kind of where we are in the Milky Way. Remember, we're moving around, even though, so that's within the next 500 years. We don't have anything to worry about. Betelgeuse is the closest star, but who knows? In a million years, we'll be on a different part of the. Not all of the stars are rotating around the Milky Way in the same way we are. So maybe someday we'll be even closer to a supernova. But so far, we don't see anything to worry about on the horizon. And we'll have a big show. And I say, it could happen tonight. Betelgeuse could go supernova tonight, or in a window's about 500 years. So sometime between now and 500 years, that's the uncertainty on when that star will go supernova. That's how they die, as we mentioned last week. When stars die, they don't just slowly fade away. They explode. Ours won't, but it's not going to slowly fade away either. So that brings me to planets versus stars. I mean, we learned about that last week, that they're different. But the ancients didn't know that. You can't tell just by looking at them on one night. Probably until you took this class, you thought that all those bright objects were stars. And right now, the brightest one that you see is Jupiter. That bright orange light in the sky in the south, right after dark, probably the first star you can see is actually Jupiter. And wait a month from now, you're going to, if you've never noticed it before, in about a month, uh, Venus is going to start appearing in our night sky. And there'll be UFO, the first couple of nights, there'll be people thinking it's a UFO. They'll call the police. It's so bright that it kind of takes you aback. It takes me aback. I mean, I know what it is, but the first night I see it, it's pretty awesome. And then Mars in the morning. Right now, we can only see Jupiter and Saturn, even if you get up early. But in about a month, if you get up early, you get to see Mars and maybe even Mercury if you really get up early. And then at night, we'll have Jupiter and Saturn and Venus, all in all very, very bright. And the ancients actually figured that out. Notice I just mentioned kind of that monthly is that's different from the constellations. They realized that the planets move through our sky much more quickly than the stars do, much more quickly than that normal seasonal pattern of our motion. In fact, the Greek word for planet means wanderer in their language, and so they realized that they moved around differently than the stars did. For your information, where I don't expect you to make detailed charts of the sky, but when you look at these, notice that the planets. I mean, you will. They don't twinkle the way stars do. The stars actually, that twinkle twinkle little star is a real thing. We'll talk about it's a bad thing for astronomers with telescopes, but the planets don't do that. The light doesn't get scattered as much, or there's more light, so the scattering doesn't change its appearance as much. It's a better way to explain that. So the planets don't twinkle, stars twinkle, but more importantly, for the ancients anyway, the movement of the planets was much more fast and more erratic than those of the stars. So they tried to come up with an explanation for that, and in order to try to understand the motions of the objects through our sky, maybe to your chagrin, they invented mathematics. They invented geometry, trigonometry. They made significant contributions to our understanding of how things moved on the Earth, how things moved through the sky, and they invented mathematics to explain that. They, however, did not believe in the cosmological principle. Remember, we learned the cosmological principle is that the laws of physics are the same on Earth and as in the anywhere in the universe, on the moon, on another planet, or just in space. How things move in space should be the same as how things move on Earth. The ancient Greeks did not believe that. They thought there was Earth, and then things moved in a straight line on Earth. If you kick a ball, and it's going to move in a straight line on Earth. But they saw the objects in the sky moved in a circular pattern. So they thought the laws of physics were different. They thought that was heaven up there, that things were different in the sky than they are here. And their models, their models took that into account. Actually, the man before his time, Aristarchus, his model of the universe. One of the things the ancients, they had no idea. In fact, even modern scientists had no idea how far the stars really were away until about 1920, believe it or not. So our description of the universe, we said it's billions, if not trillions, of light years across. The ancients, with their eyes, they saw Jupiter, and then they thought the stars were just a little bit further away than Jupiter was. And so kind of as we go through this history, the universe is just going to keep getting bigger and bigger and bigger and bigger. Uh, but to the ancient Greeks, the universe was the size of the solar system, and the stars were just uh, we learned about the celestial sphere as a way to kind of navigate ourselves around the sky to tell where something is. They literally thought it was a celestial sphere, and the stars were maybe just kind of many of them described them as holes poked in the sphere, and that the light from the ultimate heaven was shining through the holes that we were seeing. And so, but they still tried to describe how this the celestial sphere operated. And Aristarchus put the sun at the center, not the earth at the center. That's called a heliocentric model. Helio meaning sun. The centric means at the center. So heliocentric model. This was the first heliocentric model that we know of. Everybody before that had the sun at the center. Aristarchus thought that the mathematics worked better with the sun at the center, and he was right. Unfortunately, I mean, this was a couple hundred BC or BCE. He didn't. His model was not accepted by anybody for two pretty good reasons at the time. I have to say, even though we know it's correct, the objections with the technology at the time. These are pretty good objections. One is we've already talked about. It does not appear that we're moving. So how are you going to get around that? As I said, they didn't have smooth train rides or airplanes, flying at cruising speed. And the other one is a thing called stellar parallax. Stellar parallax. Let's do it together. Let me tell you what parallax is. Not stellar parallax, but if you put your finger in front of you and you focus on an object that's a little bit further in the distance, and then either blink or slowly move your head back and forth. I can't blink with my right eye for some reason, so I have to move my head. But you can just blink. You'll notice that your finger looks like it's moving. Hold your finger still. Don't move your finger. Move your head back and forth or blink. It looks like it's moving, but the object that is in the more distant object is not going to move as much. And then next time you're outside, do the same thing, only focus on something very far in the distance, and you'll notice it barely moves at all. But it does move. If you blink your eyes or you move your head back and forth, those objects move. Well, in this model with the Earth rotating around the sun, that's kind of like you moving your head around, and so you should be able to see the star, not move a lot, but it should be in a tiny little different position, like that tree is when you blink your eyes when you try this out at night. The rest of the scientific community did not said, "What is this?" Aristotle, in particular. He said this model can't be right. Where is stellar parallax? Why can't we see the star move a little bit? If we're really rotating around the Earth, why can't we? Rotating around the sun. I got my brain I'm thinking like Aristotle now. If the Earth is really moving around the sun, why can't I see the stars? The stellar parallax. Why don't they kind of move a little bit? So he went back, made his model of the universe. You can see it here. They knew about all the planets. So it's got Earth, and then the Moon, and then Mercury, and then Venus, and then the Sun, then Mars and Jupiter and Saturn. Other than this being in Latin, those names are still the same. We keep the same names. And then you can see the constellations here. Kind of slowly rotating around the Earth, why we see different constellations at different times. Again, their cosmology, it worked pretty well. This model, if you're just using your eyes, works perfectly fine. As I said, the Babylonians could, to do an eclipse, all you have to know is a relative motion between the sun and the moon. And so this model worked very well. This model worked for thousands of years, actually. Um, but the first kind of wrinkle in this, or the first thing that this model did not predict easily, was a thing called retrograde motion. And remember, I told you that Aristotle, the ancient Greeks, thought that the natural motion of an object in the heavens was in a curved circular path. Well, if you keep close track of Mercury or Mars, this is a picture of Mars, any of the inner planets, I mean, all of the planets do this, but you have to be extremely patient to see this with Jupiter or the outer planets. We'll learn that they go across our sky much slower because they're further away, but they're actually moving slower as well. So here's a picture of Mars taken like every 3 months. And notice something interesting here. This is a time you may not get, you can probably get a feeling for it, but let me show you the time on this time lapse. It's Mars appears to stop and then kind of slow down, stop, and then go backwards. Not natural to anybody, even the Greeks. And then it slows down again, and then it comes backwards this way. So this retrograde motion was very difficult to explain with the geocentric model. It did not fit into what Aristotle's any of the stars don't do this. That's kind of I mean, they knew the planets were different before they measured retrograde motion, but this did not fit in his model easily anyway. And so he went back. He said, "Look, maybe my man Aristarchus was right because you don't have this problem. It's not a problem if the Earth is in motion around the Sun and Mars is in motion. It's just that they're moving at different speeds." And again, this kind of like if you're moving at 90 miles an hour and there's a car in front of you going 60, it's going to look as you get towards it, it's going to look like it's slowing down and coming towards you. But then when you get past it, it's going to look like it kind of changed direction, and now it's moving away from you, and it's getting faster away from you. So this retrograde motion is naturally explained with the heliocentric model. It's just that the Mars and the Earth are moving at a different speed. Aristotle figured this out, but he said he could not get away from the stellar parallax, and he actually wrote this down. His biggest blunder, and he was a fantastic scientist, but he let this bias get to him. He said that the stars would have to be unfathomably far away to avoid stellar parallax. Well, guess what, folks? The stars are unfathomably far away. And so he had no measurements that they were close. It makes sense that they might be close. Why would he? I mean, how could he make that leap? But he had no proof. He had no evidence of how far away they were. And so he let that bias kind of cloud his model, and we were stuck with this model for a long time. Let me take a step away from the ancients and tell you how the scientific method and how we would deal with this. And actually, I'll give you an example of how we're dealing with this today. Not with this example, but a similar example. So the scientific method would say, well, I have two models of the universe. One of them explains this retrograde motion correctly. This motion of Mars correctly, but we have this stellar parallax problem. But one of the answers, one of the hypotheses is, well, maybe the stars are a lot further away than the planets are. And then we would have gone out and we would have tried to test that hypothesis. That's not what happened here. So the modern day equivalent to that is dark energy and the fate of the universe, and a measurement of a parameter called the Hubble constant. It turns out the Hubble constant may not be constant. In fact, we have measurements on it being different. The Hubble constant, we'll learn all about it, but it explains the expansion of the universe. And it turns out the universe is not only expanding, but it's accelerating. The expansion is speeding up. And that is, we'll learn, that's dark energy. That's actually the evidence for dark energy. So one of the things that, one of the reasons one of the things we want to learn about the universe is, how is it going to die? How will it end up? Uh, Probably well beyond our lifetimes, unless, who knows what our lifetimes will be, but well beyond our present lifetime. Um, to put yourself at ease, we have, all of the models say we have trillions of years before we have to worry about anything, well, as far as the universe goes. As I said, we have billions of years to worry about the solar system. But by that time, hopefully, we'll be able to leave the solar system. But we have, we have trillions, if not trillions and trillions, and if not, maybe forever, that the universe will be livable. But because I don't know the true nature of dark energy, we actually have three different scenarios, three different models of how the universe go, that are based on what dark energy will be. The ancient Greeks could have said, well, let's continue on with the geocentric model. Let's do the heliocentric model and see what it predicts, and see if we can figure out if we can where the stars really are, and help have that guide our way. But they didn't, and so we were stuck with this geocentric model for thousands of years, literally thousands of years. And we just kept trying to rationalize it, try to figure out how to explain this retrograde motion. So the next in line was Claudius Ptolemy, and or Ptolemy, depending on your. I don't. He was Roman and Egyptian, so even scholars are trying. It's not clear how you should really pronounce his name. Um, the And so one of the things I want to note, we had to in this history of astronomy, there's these gaps. Unfortunately, the thing that kind of evolves with civilizations in their technology, their understanding of the universe, seems to be going to war. So either massive earthquakes or war, or both, killed the Greek civilization. And the Romans were way busy fighting wars to really get into astronomy. So we have this gap for hundreds of years in our knowledge of the heavens. And unfortunately, we're going to see these gaps keep going on, and hopefully we won't have one our own selves. So the next in line was Ptolemy. He made an elaborate model of the again sticking with the geocentric, but kind of, again, this cuckoo clock arrangement, whereas rings upon rings. He called them epicycles, where they wasn't so everything was still orbiting around the Earth, but all of the other objects except for the moon and the sun were kind of like on these gears that not only did they orbit this way, but they spun around some kind of axis, a pivot point. There's nothing there in his model, except some invisible gear or something, or a piece of rope that they're being swung around. Who knows? Again, it was just like the mechanical universe to them, trying to, it was like a machine up here. So it turns out that this model explains retrograde motion. Once you measure it for one object, you wait around, 20 years. And again, they were very patient. Luckily, we had star charts going back to the Babylonians that were preserved. Actually, Ptolemy was in charge of preserving all of the measurements from the ancient astronomers. Had this giant book in this amazing museum in Alexandria that kept track of all of the scientists and measurements before him, and this was his model of that. But then the Romans and Egyptians went to war, and astronomy, another 100 years or so, 200 or 300 years or so, actually, The mantle was taken up by the Arab astronomers in what's now Iraq. Yunis al-Hassan and al-Satir made tremendous strides in our understanding of the heavens, of the stars and the planets. They built instruments, not telescopes yet, but they built devices that allowed them to make more precise measurements of where the stars are, where the planets are. The Greeks had started building devices, and they've been used for navigation, but these were even more sophisticated, and they allowed more precise, not just the devices before this were trying to tell you where you are in relationships to the stars. These we're getting a better measurement of where the stars are and where the planets were. And they started to realize that, the stars do seem to be further away than the planets, much further away than the planets. They still had no idea exactly how far away they were. They started to question the Ptolemaic model. Yes, it worked okay if you're just trying to tell me where Mars will be sort of in the sky in a month. But if you really want a precise measurement, it's not giving me a precise answer that's correct. It gives me an answer, but it's not correct. So they started to question this. They questioned the geocentric model. They started, I don't know if they ever wrote it down. It's a point of contention whether they ever wrote down a heliocentric model. They certainly alluded to it, that perhaps this would be better in a heliocentric model, but they never wrote it down, so they don't get credit. But they certainly laid the groundwork for us going back to the heliocentric model of the solar system. The person who gets credit for it, and rightly so, at least giving those caveats, we'll learn that whoever writes that paper is what we remember as a society in the history books. But the scientists, we realize the contributions of everybody. So you probably learned in grade school that Copernicus, came up with the heliocentric model. He certainly was the next one to write it down. Remember, Aristarchus was the first one, way back in 350 BC. Right? Check this out. I mean, we're in 1500 AD now. That's thousands of years, not just hundreds. That's thousands of years. We go back to the correct model. But he was so afraid. He was a priest. That may seem ironic. It's not, however, because this is Europe after the Dark Ages. So whatever, I mean, remember in the Dark Ages, there was no science, there was no education. In fact, it was scarily enough, it was anti-science. Sound familiar? That's what's they burned books. They didn't listen to anybody. They didn't listen to the science. They were ostracized. But even as they started to come out of that intellectual coma, the Catholic Church reigned supreme. There was no separation from church and state in Europe. There was no separation of church and education. All of the major universities in Europe were run by the Catholic Church. And so I wrote ironically, there was a Polish priest, but it's not really that ironic. The priest actually had to study astronomy. It was one of the seven disciplines they had to learn to kind of keep their minds out of the earthly. I don't know what the right word of that is. Temptations, to really study the heavens themselves. So it's one of the things that they studied to keep away from the trivialities of man. But he realized most of the books had been burned, but somehow he had a copy of one of Ptolemy's encyclopedias. And he realized that the universe could be well better explained with the sun at the center. So this is his model, Copernicus's heliocentric model. Again, it's in Latin, but the names are all the same. He's got the order of the planets right. He's got the time it takes them to make their orbits correct. He realized that the inner planets are moving faster than the outer planets as they go around. He realized that this explained, and he was able to predict retrograde motion. For Mars, for instance. This is what I was speaking to you about. The Earth is moving faster. The objects that are closer to the sun are moving faster. We'll learn the physics of that. Again, it's going to take another. It's going to take another 100 years, not for me to explain it to you, but for our history. We're going to wait till next week to actually learn why the Earth goes around faster. Hopefully you already know why the Earth goes around the sun. I'm pretty sure I mentioned it. If not, hopefully you know. If not, think about it. Why does the Earth orbit the sun? What magical force keeps us from just going off into space by ourselves? But anyway, we are moving faster than Mars, and so if we kind of line up where Mars looks like, we get this weird pattern in the sky. So his model explained retrograde motion of the planets much better than inventing these gears or whatever. But I mean, honestly, the Ptolemaic model is pretty cool, right? And if you really think there's a machine, why not? Why not have them orbit around on the gears? The one objection as a modern scientist I would have with the Ptolemaic model is this. Why in the world they all seem to be orbiting around these epicycles except for the moon and the sun? That would leave a little bad taste in my mouth. If everything I saw was rotating this way, it's like, well, what happened? Did the gear break on the sun or on the moon, or why doesn't it do the same thing? Now again, there was probably some mysticism associated with that. The sun and the moon were certainly more important figures in the sky as far as religion goes. So perhaps you could explain that away. As a scientist, that would be the only explanation. And as a scientist at the time, I couldn't say. Well, I would say, well, yes, Copernicus' model is simpler. But really, does it do a better job? Simple is not always the best. There is a principle called Occam's razor that says it says the simplest answer is usually the correct one, but history is filled with exceptions to that rule. It's not even a scientific rule. It's just something that seems to be true. But we're going to learn the two things that break that rule spectacularly. Quantum mechanics, one of the greatest achievements and the greatest theories of humankind, is not simple by any means, nor is general relativity, what we'll start learning about next week. Neither one of those are very simple. So we're not just going to say the simplest model wins. What we will say, and what they did, remember the scientific method was in full effect at this point. If you could get out of the religious haze, they knew how to do science here. So what do? We go out and we make some measurements. And we, being one individual, pretty much, it's called Tycho Brahe. He pretty much lived on this island, and he spent 25 years building better devices, still not a telescope, but better ways to more accurately determine the position of the stars and the planets. So he took years and years and years of data, and lo and behold, neither one of those models worked, and neither one of them were any better than the other. Copernicus's model of the universe did not explain the actual movement of the stars in our sky any better than the Ptolemaic model did, actually. The only thing it had going for it was explaining retrograde motion easier. more naturally anyway. So 25 years of measurements, and we cannot decide which one of these models is correct. Tycho, in his frustration and perhaps his health, enlisted a German mathematician named Johann Kepler, who had no interest in making measurements whatsoever. However, one of the things Tycho, he was not that he wasn't a great scientist because he did not like to share his data. He did not want to give his data to Kepler to try to figure it out. He wanted to do it himself, and he did not have he he didn't have the mathematical ability to kind of change up any of these models. He just took what either Ptolemy predicted or what Copernicus predicted, and he went out and measured. He was a fantastic observational astronomer, and he realized that neither one of them are correct. But he made a deal with Kepler. He said, if you come and work with me for 2 years, taking observations, I'll give you my data. So Kepler did. There's kind of a funny, or not funny is not the right word, an interesting urban legend that Kepler hated it so much that he actually poisoned Tycho and killed him so that he could get his data earlier or not. I'm not sure if that's true. I don't know if anybody knows if that's true. I don't know. I don't even know who. I don't know what evidence there is for that. Maybe it's just an interesting story. Don't feel too bad for Tycho, though. He was a great astronomer, but he basically enslaved everybody on that island to build and work for him. So it wasn't a great loss to humanity. It was a pretty big loss to astronomy, though. But now Kepler's got his hands on 25 years of meticulous data, and Kepler was the first data scientist. Data science is actually a career you can go into now. This is the guys at Google and Facebook and YouTube, when they predict what you want to buy or what video they want to show you or whatever. They don't care about you. They don't care about they're just looking at the data. And they find patterns in the data, and they can use that to make predictions. And so Kepler, without, again, no computers, no calculators, his little compass here, and some paper, plotting out the trajectories of the planets. Just to give you an idea, these planets take 50, 60 years to make one complete orbit. But we had a lot of data. You don't need to map out their whole orbit to actually figure out what's going on. But it was a difficult process, but he figured it out. He cracked the code of the solar system. He figured out the pattern, and we call this empirical science. When you figure something out and make a law, you don't understand. He had no idea what was holding the planets together, why one of them was moving faster than the other. But he figured out the laws. He figured out the code of the solar system, and he has 3 laws. And actually, these laws are still they still work to this day. At least for our first glance, our first a rough idea. Not even rough's not even the right word, but as long as we don't need something extremely precise, Kepler's laws actually still work to this day. We'll talk about how we have to change those laws. We'll talk about the history of how they've been changed a little bit. But his first law, the first step in cracking the code, if you go back, I'm not going to flip back to it, but you can if you like, or just recall. Copernicus's model of the solar system had perfect circles, and that's where it was wrong. Now they're pretty close to being circular, but they're not exact circles. They're not perfect circles, and so that's why they were off. You might, again, Copernicus was a priest. He probably did still think that they were heavenly objects and should be perfect, and so It was natural for him to put the orbits as perfectly circular. Perhaps if he had published this before, instead of waiting till he was dying to do it, he would have seen the light and said, "Oh, it works better if I don't use perfect circles." But he wasn't around. Uh, but Kepler was the first to realize. Kepler, with Tycho's data, was able to realize that it's not a perfect circle. They go around in ellipses, which is just like an egg pattern. And if you ever remember, you may have drawn these as a kid. You put some string around your pencil and put the other end of the string around just another pivot point, and go around. You'll make this kind of a geometric figure called an ellipse. Or if you had a spirograph when you're a kid, you did the same thing. Different gears, you would make those these elliptical patterns, and you could move that around, and you make the kind of cool clover shapes and things. You guys probably have no idea what I'm talking about, but look it up. It was an old kid's toy. We would make ellipses, called a spirograph. Okay, so they're not perfect circles. They are ellipses. That wasn't it. His second law, he said it. Remember, he's a mathematician. He can't speak in English or German, sorry. But as a planet moves around its orbit, it sweeps out equal areas in equal times. Now, that may sound understandable to you, but when I tell you what that really means, you say, "Why didn't he just say that?" But let's look at what he's saying. What he's saying is that you may not believe this. If you don't believe this, print it out and cut this up, and then cut up the red area and the blue area into little pieces the same size, or however you want to estimate how much area that is. Maybe if you're a mathematician, you can do, approximate them by some triangles. Be careful with this one. But they have the same area. This is the same area as this, is the same area as that. What Kepler noticed was that the time it takes to sweep out this area was the same. That makes no sense, right? This is a lot shorter distance to move from here to here than this. The only way that makes sense is if the planet is actually speeding up as it gets closer to the sun. And that's what's happening. And that's why I said, why didn't you just say it? When a planet travels fast, the planet travels faster when it's nearer to the sun and slower when it's further. Makes a lot more sense to me. I mean, they're the same thing. I think you'll agree that my way of saying that is better. But if not, do Kepler's. I'm not gonna ask you to memorize what Kepler said, but you do want to know that when an object that is not under its own power, it's only under the gravitational pull of the sun. I guess I just gave it away. That's what holds the planets together, is gravity. Kepler had no idea. But an object that is just being powered by gravity will move faster the closer it is to the sun than further away. We'll learn the law of gravity that makes sense in. We'll learn some other laws of the universe that also makes sense in. But right now, Kepler had no idea the cause of this. He just realized this was the pattern. This was the code of the solar system, is when the planet in its orbit, when it's closer to the sun, it's moving faster than when it's further away. So that's his second law of planetary motion. He's got a third one that he figured out. I'll have to say this one, I'm not a mathematician, but this is pretty beautifully simple. P squared is equal to A cubed. I can get around that kind of mathematics. Trust me, y'all. I dislike mathematics just as much as you all seem to convey in our first week. But I also realize that it's a piece of my toolbox that I need to learn in order to understand and to explain the universe. So this is nice and simple. P squared is equal to A cubed. No, there's no problem about it. This is the easiest equation we'll ever have to deal with. There's no constants here. There's no, there is units. I was going to say there's no units you have to cancel. But this simple formula, you actually have to, the units don't make sense in it. But again, this is an empirical law. This is a pattern law. If you measure the orbit, the period, and the period is just how long it takes to go around the sun, and you square that, and then you measure the average distance from the sun, and you do both of those in special units. If you do the period in years and the distance in AU, recall from last week that AU is the average distance between the Earth and the sun. If you make those measurements in those units, we get this very simple formula. They're not equal, they're not, but the period squared is equal to the average distance cubed. Pretty cool. Let's test it with the Earth. The orbital period of the Earth is 1 year. The average distance from the sun to the Earth in AU is 1. 1 squared is equal to 1 cubed. That works for me. 1 times 1 is 1. 1 times 1 times 1 is 1. So it works for the Earth. It works for every planet we know. It works for every planet that Kepler knew, and it works for 3 planets that we discovered after Kepler died. So his model, as I said, to this day, explains these are modern measurements. Explains and it works. Oh, point, you can see it. There's slight deviations. We'll talk about the slight deviations between them. They're for a couple reasons that we'll discuss next week. But to a very good understanding, but understanding is not the right word. Remember, he had no concept of gravity. He had no concept of space-time. He thought it was a giant, not just a giant machine, but a giant musical instrument. When he published this, he talked about the harmonics and the harmony of the planets orbiting around the sun. But so he definitely described this. He cracked the code of the solar system. Not quite just a planet. So stars don't. He didn't have anything to say about stars as of yet. Oh, sorry, this won't work here. Look at this on our front page. Click this and you'll see the inner planets are moving a lot. You can the outer planets barely move while the inner planets zoom around. Okay. So we would think that that everybody would be happy now, but it was not. There were still lots of objections. It was not actually well received, nor was it immediately considered the proper theory. Again, let's review. This is a heliocentric model with the sun at the center, as opposed to a geocentric model with the Earth at the center. There was a huge backlash for this in Europe because the geocentric model of the universe had been written not into the Bible, but into holy books, into books that talked about those 7 disciplines, the 7 sciences, as they would say, although they weren't very scientific about it. And those could not be questions. While this was going on, Bruno, not for this reason, but he did kind of mention the universe might be a lot bigger than the solar system. There might be other animals on different planets. He was a cool guy. He got burned at the stake for thinking outside of the box, the little box of what was written in those 7 books. And so this was not well received, especially in Europe. And he was in Europe. There were some, however, and then going beyond that book, he just made the universe less perfect, right? The heavens are less perfect now. Those orbits, those are heaven up there, literally. I mean, at that point, for most of the people, he was just describing a heavenly object up there. And it better be perfect. Why is it not perfect? I don't know why you would think a circle is more perfect than an oval, but whatever. So that was not a scientific objection, but it was certainly a sociological objection. And we can't. We'll learn over and over again. The scientific method helps scientists. It may take us hundreds of years, though, because of societal pressures, even in our own brains, accepting things go beyond there. So it was not well received. There were two scientific objections, though. One was our old friend. They kind of, why don't we feel us moving? They had by this time, they had nice carriages, and they'd probably been on nice smooth rides. So they kind of know. Well, if you go smooth enough and you close your eyes, you can't feel that motion. So they kind of changed this into a different objection, which I hear to this day from YouTube on and the few of my flat Earth students that I get occasionally. That well, if the Earth is really spinning and a bird is stuck to the Earth by gravity, when it flies off of the Earth, why doesn't it fall backwards? If we're real moving 1,000 miles an hour, then why isn't it the birds fall backwards? We'll learn about that. It's because the bird is already going thousands of miles an hour. It's called relativity, not Einstein's relativity, but actually another scientist's relativity called Galileo. You probably heard about, which we're about to hear a lot more from. But that was an objection of the time. Why don't things why aren't they things in the air left behind if the Earth is really spinning so fast? And again, going back to Aristotle, we still can't detect stellar parallax. The Arab astronomers with their devices did not detect stellar parallax. Tycho, with his advancement in technology, did not detect stellar parallax. So it's still an issue. If we are really going around the sun, why don't the position of the stars move a little bit? Again, nobody, there were hints that the stars were further away, but still, it was kind of mind-boggling to the scientists at the time that they would be that far away that we wouldn't be able to detect them moving. By the way, we do detect stellar parallax today. We just needed better technology. The next step in technology was actually the telescope. Galileo did not invent the telescope, but he perfected it. It was invented by, I don't remember the gentleman's names, two Dutch eyeglass makers. I got it by accident, got a couple of the lenses, kind of together, and they realized that things got magnified. The applications of that are microscopes, but another configuration was a telescope. We'll learn telescopes don't really make things look bigger. What they do is they allow us to see things that are much, much further away. The size doesn't get much bigger, especially in Galileo's telescope. And so he sold his perfected telescope to the Italian Navy. And he used the money to make even better telescopes, and he didn't have to work anymore, so he started pointing it at objects in the sky. He was the first person to point a telescope at the sky, and it was astounding. It was unbelievable. It revolutionized the science of astronomy. He is considered the father of modern of astronomy because of his perfection and use of the telescope to actually look at the objects in the sky. But again, right, this is hundreds of years after Kepler. Here we go. So his first objection, or the first objection that he dispelled, was that these things in the sky they're not like religious Christmas tree ornaments, or they're not other perfect heavenly orbs in the sky that we can visit after we die. He looked at the sun. The sun has blemishes on it. It's got sunspots. How could a perfect heavenly object have these defects in it? He actually, and they kind of came and go. He also used them to realize that the sun was rotating. So that was kind of interesting. Not everything has to rotate around the Earth. He saw pictures of, he saw the moon. He saw mountains and craters and valleys. And I mean, to him, uh, telescopes at the time, in fact, most telescopes, except for the very, very largest professional ones, you don't actually see color through. It's very difficult to see color. Everything is kind of in black and white. Um, he realized that when he was looking at objects far away, even with his telescope. So if you imagine the Earth, I mean the moon, it kind of looks like the Earth uh, through a telescope, or if in a black and white. It's got craters. We don't have craters, but he saw the imperfections. He thought those dark areas, the man and the moon, were actually oceans on the moon. So he realized it's certainly not. It's not some perfect orb up there. It's definitely got some kind of interesting structure. It looks certainly more like Earth than some kind of Christmas tree ball. The that was not, as I said, a scientific objection, but it was an objection. And so his next getting around that was he saw Jupiter through his telescope, and a couple of amazing things. First of all, Jupiter got bigger, so that was interesting. And he started to see these other objects around Jupiter. Um, so these were not stars. They were dimmer than the stars. You can't see these with the naked eye. You can see, many Jupiter wanders around. Sometimes it's got constellations behind it. These are not stars in this picture. It'd be pretty weird coincidence that they would line up like this anyway. But not only that, and this is actually a simulation of what he would have seen through his telescope. This is what I mean. You can go and buy a Galilean telescope at Walmart and look at it, and this is what you see. You can actually see the moons of Jupiter with a $50 telescope. You can actually see the moons of Jupiter with a pair of binoculars. Actually, if it's dark enough out. But that's a good pair of binoculars, which would cost you more than a cheap telescope. But it's definitely accessible for you to actually see this with your own eyes. If any of you are in Chicago, hit me up with an email. I teach a couple of other astronomy classes in Chicago city colleges, and we have observation nights. So if you're in the area and you want to come to one of those, shoot me an email. We're gonna have one in. We're gonna have one in mid-November. We're gonna watch the transit of Mercury. Actually, it's going to get in front of the sun, so during the day we'll actually see. It won't be a sunspot. They'll actually see the shadow of Mercury go across the sun, and then that night we'll be able to see Saturn's rings and things like that. And then, we don't have fancy telescopes either. So it's a lot of this stuff is very accessible to you. If you're in California, go to Mount Wilson Observatory in the hills out above LA, and they have observation nights there all the time. There's probably others. I'll look into that. See the easiest one that still puts on astronomy nights for you. Then wherever you are, just kind of Google it. You can see the. Go take a look once in your life. Look through a telescope at one of these planets. It's breathtaking. It's not going to be as cool as the images I show you from Hubble or the satellites going around them, but just seeing it with your own eyes is pretty spectacular through a telescope. Spectacular just with your naked eye, I think, but really looking at them through a telescope is a pretty amazing experience. So back to Galileo, he noticed that these little lights changed orientation. And sometimes there'd be two on one side and one on the other. Sometimes be three on one side. So he changed. He kept track of them over the course of several weeks, and he realized they were orbiting around Jupiter. These were moons. These were tiny little objects that were orbiting around Jupiter. So not everything in the universe orbits around the Earth. We have Jupiter here. Jupiter looks like its own little solar system. And the more we learn about Jupiter and its moons, the more we're going to see. It is almost like a miniature little solar system. Not to give away the ending, but if Jupiter was a little was about 10 times more massive than it is now, it would have turned into a star itself. So it's like a miniature solar system orbiting our sun. We'll talk a lot more about that. The other thing that you don't see in this picture, we should have had one with the, is that the stars. So through his telescope, the planets got bigger, the moon got bigger. He could see the moons of other planets. Guess what did not get bigger? The stars. The stars did not get bigger at all. And he's like, wait a second. If every if Jupiter gets so big that I can actually see its rings, then the stars really do have to be a lot further away, unfathomably far away, as Aristotle would say. So he overcame. He did not. He set out to measure it. He's like, well, I got my new technology. Maybe I can measure stellar parallax. But no, you need a much more powerful telescope than what Galileo had to actually measure it. But he put it together. They are that far. I shouldn't be able to. I should be able to measure it. They're so far they don't get bigger in my telescope, so they got to be. They have to be that far away. Um, so he overcame that objection. We're going to save the other objection till next week, when we talk about how things move. But he actually also overcame this, why things are left behind. He came up with Galilean relativity. We'll talk more about that next week. Um, we'll go back to Aristotle and talk about how Galileo changed things. Uh, let's finish up this lecture with what happened with just Galileo. Galileo did strike the last nail in the coffin of the geocentric model, and that was with his observation of the phases of Venus. When you see Venus next month, it's going to just look like a very bright light. As I said, so bright you probably think it's an airplane or a UFO. So you cannot see the phases of Venus with your naked eye, but through a telescope you can, and it has phases just like the moon. And in fact, it's the same reason. If you haven't gone over the phases of the moon this week yet, come back to this after you've seen these. You'll notice the names are the same: crescent moon, gibbous moon, full moon, new moon, quarter moons. Venus goes through phases because of the relative position between Earth and Venus and the Sun, the same way the moon does. Well, if the Earth is actually stationary and Venus is orbiting around its epicycle that it needs to do in order to explain retrograde motion, or even if it's not doing anything like that, even if it's in a regular circular motion, you don't get phases. You don't even get full Venuses. All right, you get the new phase where you can't see it, and then you get the crescent phase. Nobody really thought about that before, but now there's no way. There's no way that Venus can and the Sun both can be orbiting around uh, uh, the Earth. You can't have the phases. You either get crescents or you get news. You can kind of explain away the reason why you can see it at all, because you say, well, Venus is moving faster than the sun, and so yeah, you'll always be able to see a little clip of this, but you'll never get to see a full moon. Sorry, a full Venus. So this pretty much killed the geocentric model of the solar system. So you would think they would be holding parades. Galileo, and this was Galileo wanted to be the rock star of science and astronomy. And unfortunately, that's not what happened. There were no parades for Galileo. For all of his hard work and development of our understanding of the universe, he got called before the Inquisition. He whether he was tortured or not, he was certainly psychologically tortured. The Inquisition was the ancient equivalent to a physical manifestation of an IRS audit to the day back in the day. So he was held. He was forced to recant everything he said. He had written 2 books about it. He recanted them. They burned all copies of that book. He would have been burned himself, except he was a frenemy of the Pope. Even so he was, and he was put under house arrest. There's some, again, the historians will say part of this was Galileo's fault. It wasn't so much that he had written something that was kind of going against those holy books, not the Bible again, but those holy books, but that he tried to reinterpret it in terms of religion. Kind of, he's like, well, I'm going to tell you the real religious reason behind this. And that did not sit well with the Pope. But he was friends with Pope before that, and so he didn't kill him, but he put him under arrest. And so he did, however, as we said, he was never allowed to look through his telescope again. Imagine discovering all of this stuff and then not being allowed to look through your telescope again. His house arrest was pretty nice, though. I've been there. An amazing Italian villa with a huge backyard's not the right word. I don't know what the right word is. It'll come to me after. So, estate. He had a giant estate. And so that's going to be important for next week. His giant estate actually helped understand the universe. But let's finish up here. Let's finish up with what we learned tonight, today, and what we learned as a race, as humans up until this point. On the backs of many ancient scientists, Copernicus came up with a model, a heliocentric model with the sun at the center and the Earth moving around it. Remember, Aristarchus started that, but Copernicus brought it back to life. Tycho spent years taking measurements, trying to distinguish between that model and the geocentric model. It did not. He couldn't figure it out, and so Kepler actually came and took that data that Tycho took and came up with his laws of planetary motion, which are laid out here for your review. And then Galileo stepped in, a couple hundred years later, and proved the geocentric model could not work. And finally, even after his recant, after he recanted it, enough of those books had gotten out that people had it and seen it and realized once you see it, once you see the phases of Venus, as a scientist anyway, then even if you want to put your religion in there, you got to think, and I've actually heard this, I've had philosophical arguments where, I see an observation and people that goes against religion and say, oh, that's just the devil trying to fool you, right? You can't argue with that, but that's kind of that's the only way you can explain the phases of Venus if you want to keep this model. The modern thing is that there, we rewrote the history books and NASA, is making fake phases of Venus pictures, just like our fake moon landing. There's still people who, want to cling to whatever ideals they have. I think most of it today is just trying to be cool and be counterculture to. There's been kind of this Kyrie Irving spike in, oh, it's cool to think that the Earth is flat kind of thing. But if you really think the Earth is flat, go get yourself a telescope and look at the phases of Venus. I guess they could still be flat, but you're going to have the flat Earth orbiting the sun. That's part of the model. The flat Earth model is that the sun it doesn't orbit the Earth, It kind of goes around in a circle. I mean, it's a pretty interesting mythology. I wonder if any of you, there's going to be one of our assignments where we get to choose a model of the universe. I wonder if any of you will choose the flat Earth model. You don't have to believe in it. I mean, it's I can poke a lot of holes in it if you really do believe it. Just let me know. I have a picture I took myself that disproves the flat Earth. Anyway, I digress. But that's what we learned. We will take this. What we haven't learned, however, well, it's not on there. Remember, at the end of these lectures, there's little mini quizzes that you can go through. This is what we haven't learned. Why? Galileo went to his deathbed not understanding why the sun has this pull on the planets. You know, why is it? Is it a machine? Is there some force in nature we don't understand? It is a force in nature, and it's an obvious force in nature, but they did not understand it. Galileo, we're going to learn next week, helped us understand gravity, but he did not put it together that is actually why we are stuck to the sun is because of the gravitational pull. But more on that next week. Good work so far this week. Keep up the great work. And remember, there is another recorded lecture on those patterns in the sky. Kind of goes into the seasons and the phases of the moon and eclipses and constellations and such. So watch that as well. All right, I will I'll keep talking to you virtually, and then I'll see you on video next week.